everybody. My name is Simone Ebna, and I'm working in Cineca as a OpenFOAM expert and a visualization engineer. I am the service leader of In-Situ visualization in Prace. So today I will present the current status and what we have done in the current implementation of Prace, and in just as a brief recap of what we have done in the previous implementation. So the presentation is technical, I know, and I assume that you know what is in-situ simulation. Miguel already described in the first slide what an in-situ simulation is, so I think that for all the people who is listening, the message is clear. So we can move to so in Prace we want to release a service for in-situ visualizations, and we achieved to reach this the following goals for the project. So we want to evaluate the feasibility of the deployment and the performances of 3 different in-situ frameworks in 3 different areas, which are the Catalyst in-situ framework released by Kitware, based on ParaView and VTK. And we couple with a plethora of safety codes I will describe in the next slide, which are. Then we try to test the features of a new framework developed by In-Situ, so in France, which is called Damaris, which has been coupled with a French code named Code Saturn. Finally, another framework released by In-Situ, which is Melissa, which works in a different area, which is a framework used for in-transit and in-situ in-transit processing of data that comes from ensemble runs. So the idea is to deploy these frameworks on Prace machines, at least 3. We are testing the framework using realistic use cases to see if we can release them as a service to the Prace community in the next implementation. We agreed internally that for this implementation, it's enough to deploy the frameworks on 3 different clusters, or 3 different sites, since we have one site can have more than 1 cluster. So if, for example, in Cineca, we tested Catalyst on Galileo, which is our tier 1 cluster, Marconi, which is the CPU-based tier 0, and Marconi 100, which is our tier 0 GPU-based cluster. Damaris has been tested on the Oak cluster in HRS. And finally, Melissa on Jewels, hosted at Ulic. So regarding Catalyst, we make a lot of testing and deployment and we instrumented the following codes: Migale, PlumeFD, OpenFOAM, and Streams. Migale is not open source, but has been used for many papers by the team of Colombo and Bassi from the University of Bergamo in Italy, which is a particular CFD code which use discontinuous Galerkin discretization with an adaptive high-order polynomial. Then we adapt the PlumeFD code, which is a DNS incompressible code developed by Pierozzoli from University of La Sapienza. Third is OpenFOAM, which is a well-known open source finite volume CFD code used particularly in engineering simulations. So its target is industrial, mainly industrial simulations. And finally, streams, which is a DNS code for of compressible turbulent flows. Normally, it's used to make DNS simulation of boundary shock interaction. So as you see, there are 4 codes. One comes from the engineer world. The other 3 are more research codes. So the activity consists mainly in the development of an adapter, which is needed in order to communicate the safety codes with the framework, because you need to in some way to talk between catalyst and the safety codes. You need to exchange information between the simulation and the rendering backend. So since normally the code is written in a language which is different from the one used in BTK, you have to develop an adapter with a mixed language. For example, normally is Fortran for the in-house research codes, and C++, which is the language of BTK. So VTK is also developed by Kickware. So CMake was is the building system used by VTK. So we use CMake also to update the building system of all the safety codes. And then the activity will continue to develop, to install all these codes and catalysts on our machines. Here I report some numbers of only the activity regarding streams and catalysts. On top you see an image, a rendering of the simulation of interaction between an oblique shock with the boundary layer. We perform these simulations on our Marconi 100 cluster, and we make some tests in order to see the impact of complex VTK pipeline on the simulations. We tested in 2 different configurations, a small one and a big one. A small has 200 millions of cells, while the big one is around 9 billion, so it's very huge. Also, the number of GPUs used are different. In the small one, we use only 8 GPUs. In the big one, we are using 512 GPUs. The frequency of when the backend is called is high for this simulation, is around 50. So it's called catalyst is called one every 50 time iterations. And as you see, the time spent for making a slice, a contour, and the rendering is not negligible. For the small one case, with a frequency of 1/50 is around 26%, and increased to around 50% for the big one case. A technical observation is the following. We try firstly to, so we are, the Marconi 100 cluster has a Power 9 architecture and Volta GPUs. So we firstly test the OS Mesa implementation plus LLVMPy, but this implementation is not stable with a huge number of cores and GPUs. So after a discussion with the NVIDIA guys, we updated the software stack using the EGL and CUDA 10. So using this stack, we fix all the issues with the DLL1 MPI. What we are testing now is to work with the VTKM filters, which are the GPU implementation of the normal filter that you found in ParaView, in order to reduce the memory transfer between GPU and CPU. This is an ongoing work, and I still don't have results to show, but probably we are planning to release a paper in summer. So if one is interested to see better results, yes, we have to wait for another 4 or 5 months. Regarding OpenFOAM, we started a collaboration with ESI around 2-3 years ago, and so we co-developed an adapter to make in-situ in OpenFOAM using Catalyst. As I told before to Miguel, we released in a module named Visualization, where we collect all the stuff that is used by OpenFOAM to make in-situ simulations. So it can be nice also to add the new adapter for the PACAT framework. What we have done in Prace are normally are two adapter. One that works with Catalyst and ParaView. The other one is that works with VTK directly without using the Catalyst API. So the question is, why you release two adapters that are based on VTK? The reason is how you pilot in OpenFOAM this in-situ backend. If you're using Catalyst, the visualization is driven by Python files that are constructed using the ParaView GUI. So you have a Python script where you call the API, the Python API of ParaView. So it's required from a user perspective to know how to pilot an OpenFOAM simulation, how to pilot a visualization in using Python VTK. So ESI decided to release a new version that is based on VTK native and is pilot using the OpenFOAM dictionary. So using the native language of OpenFOAM, so which is nice for from a user point of view. Here I reported some links that one can because the code is too long to be shown in a slide. But if one is interested, can click on the links and see the differences between these two approaches of using Catalyst and OpenFOAM. Recently, I think a few months ago, Intel presented at the IEEE Supercomputing Conference a demo where Intel showed the performances of OpenFOAM plus Catalyst for in-situ temporal caching high fidelity visualization using its hardware, its new hardware, which is Intel Optane and OSP Ray. You know, OSP Ray is a technique that uses rendering via CPU, and Intel Optane is a particular memory developed by Intel that has size more similar to an hard drive, and the performance is more similar to the RAM memory. So the idea is that the user runs the simulation on the cluster or on a workstation that has this Intel Optane, and it can go back and forth during the simulation, because all the time steps are saved in memory. Since this memory is so big, it can contain a lot of in-situ time steps, and the user can throw them by without making any storage on the hard drive, but it stores them on the Intel Optane memory. So it's an in-situ in the Intel Optane memory. This is a screenshot that taken from the Propeller tutorial, which is you can find it in the standard release. In parallel, HLRS is helping me to develop recipes in Spark. Spark is a package manager that now is used by many HPC centers to easily the installation of tools, and so we work together with HLRS to develop recipes for OpenFOAM, for Catalyst, in order to install all this in-situ stack in a singularity container. So we finally get it. So we have this Spark recipes to create an in-situ container, and we are working to test the performances intra and inter nodes to see if there are differences between using in-situ in a container or not. This is an ongoing work. We still don't have results on this. The guy that is working on is due in the near future. So last part is regarding Code Saturn and Damaris. Code Saturn is more similar to OpenFOAM. It is a safety code used for engineering problems on unstructured meshes. IRIA is I decided to use a different framework, which is Damaris, which has a completely different approach with respect to Catalyst. And I reported here a brief description of the main feature of Damaris. As I written here, is an in-situ framework which leverages dedicated I/O cores on each multi-core node, along with the use of shared memory to perform asynchronous data processing and I/O. So while Catalyst has a synchronous approach and use MPI to communicate, here we are inside the node. We use shared memory approach, and the visualization is done in an asynchronous way. So it's targeted for the new multi-core node that you found on cluster, where you have normally more than 10 cores per node. We are installing this code on the Oak cluster. So it's an activity that started a few months ago. So they are developing an adapter for making communication between Damaris and Code Saturn. The idea is to test the frameworks with an order of thousands of cores. So here is a slide that describes the architecture of Damaris, where you see you have you see the architecture of a SMP node, where most of the core are dedicated to computation, and a few of them are dedicated to visualization. They works, as I said, they make the co-processing asynchronously and communicate with the compute core via shared memory, so no MPI. This approach cannot be pushed by Catalyst. So if one wants to, in some way, emulate this behavior, talking with the previous developer of Catalyst, which was Andy Bauer, if you want to make something similar, you can use the aggregate dataset filter that combines the data from multiple MPI processes onto less MPI processes. So the idea is that the cores that participates to visualization are a part of the course that participates to the computation, not different ones. And also you use MPI to communicate and not share memory. So I hope to have at the end of Prace6IP some numbers to compare the differences between these two approaches when you go when you use a lot of number of cores. So the last one is Melissa, which is, as I described before very briefly, is a framework for large scale, so targeted for HPC, in transit. It means that no files have been written on the hard drive. Processing of data from ensemble runs, so it means that you run different instances of the simulation with different set of input parameters. So you are sweeping the input parameter space in order to enable sensitivity analysis. This framework has been installed in Prace on the Jewels machine, but has been also tested on many French ones like Genze and Oxygen. A first prototype of this framework has been tested with 16,000 of ensemble members and 16,000 cores. INRIA is planning to release soon a paper to describe all these results of this framework, which is released not too much years ago. And in Prace, they work a lot, in particular in software engineering aspects like support containers, which is now a nice word, a buzzword, and also on also on the writing and testing the framework on different architecture using unit test. So this activity is as I always said, is a never-ending activity, because we continue to test and deploy the frameworks on the machines that will come. For example, in Cineca, the pre-exascalar machine named Leonardo will be ready probably at the end of this year. So we are when we'll be ready, we start to port all this activity, all these codes there, and also for other machines that will be ready in Prace. So the idea is that at the end of the 6 implementation and in the next one, we want to make available all these frameworks for the community, and also to make available the adapters of the safety codes that are open source and used by scientists in Prace. Okay, I think it's enough for today. Hope that everything is clear. Otherwise, you can ask me